restart this. Okay, so here we go. PV diagrams, pressure volume diagrams. So pressure will be on the y-axis, volume will be on the x-axis, and we're going to show you each of those processes because it's been a while since we talked last. So we're going to do these in different colors. Our processes are isobaric, isochoric, isothermic, and adiabatic. So we've got to be able to recognize on a graph, we need to be able to recognize on a graph what the shape is so that we'll know which kind of process it is. So we're going to match shapes with names today, and then we're going to start doing some math with it. But mostly we're going to just do the shapes and interpreting the graphs. So we'll see how far we get. Okay, so isobaric means what? You remember? What does a barometer measure? Pressure. So isobaric is a constant pressure process. So an isobaric process on a PV diagram would be a horizontal line. So isobaric would be A to B. You stay at the same pressure the whole time. Okay. Process number 2. Isochoric. Constant volume, because isothermic is constant temperature, so the other one's got to be volume, right? So isochoric is a constant volume. This would be B to C. So those would be vertical lines. So horizontal lines and vertical lines, isobaric, isochoric. So what is isothermic going to look like? Isothermic is going to be curved. It's going to have that sort of exponential curve shape to it. So this would be C to A. And I'll tell you how to check for an isotherm versus an adiabat here in just a minute. But the adiabat is going to sort of look like this one, but it's going to be much steeper. That would be A to D. I'll give you a minute to get copied, and then we'll talk about how to separate these two. How do we tell the difference?
So what changes in your option?
Say again?
What changes? That makes life so sweet.
It's because it's changing, all of them are changing. Pressure, volume, and temperature are all changing. So you don't get that nice smooth, I cut it in half on this side, so I doubled it on that side. Okay, you lose the proportion relationship. So you can tell an isotherm because it is inversely proportional to. Inversely proportional between pressure and volume. Adiabats aren't too steep. So isotherms P1V1 equals P2V2. So if I make this one go down, the other one has to go up by the exact same amount. Okay? Change in pressure is 1 over the change in volume. So if you see like the pressure doubles, if the pressure doubles but the volume triples, you don't have a isothermic equation. If the pressure doubles and the volume halves, you have a isothermic. And I'm going to show you one other thing about isotherms, and then we'll start practicing classifying them, and then we'll get into what do you use them for. So I'll wait, because I know everybody's kind of still copying and stuff. So all the students I didn't know before this year, all of you I'll recognize without your mask, but all the ones I have in Physics 1, I'm not sure I'm going to recognize them without their masks. We're like, oh, that's what your face looks like. Okay, so since isotherms are constant temperature, so how do we know, how do we estimate the temperature? So PV so if these are all isotherms, the temperature increases as you move this way. So this might be 100 Kelvin, 200 Kelvin, 300 Kelvin, 400 Kelvin. So they all have that same shape, but the further away you get from the origin of your XY axis, the higher the temperature will be. So as I slide from here out, the temperatures are going to be getting larger and larger. And then last but not least, the math pieces, we're going to use the three pieces of math we use with this. 3 formulas or relations. We're going to use what's called the combined gas law. We're going to use, so this is the combined gas law. Actually, there may be 4 of these. Let's change that. We're going to use the ideal gas law. which is PV equals nRT or nKT. So this is the one we use the most. The second one we use the most is the first law of thermo, which is delta U equals Q plus W. This is the other one we use. This is the first law. And then delta U is 3/2 KT. So lots of notes to start today. I'll leave that up for just a minute. I'm going to get some cold caffeine. Where's my, oh, there it is. Okay. There we all are out there. Remember that internal energy, delta U is internal energy. So the two we use the most are the combined gas law and the first law of thermo. Okay. So everybody with me to here? I mean, I know you don't know how to use any of it yet. That's okay. But you need me to scroll up or you've got what you need? You good? Okay. All right. So you're going to see that I have a ton of thermo questions. Okay. Stop. Okay. I don't think I want to do multiple choice to start with. I think I want to do free response, since I need to be explaining what we're doing. Okay, so I don't expect y'all to copy these, but I'll have them on the video. So you guys out there in distance learning land, I'll have the video. I'll post it tonight on my YouTube channel so you can go back and look at the questions. So we have a graph here that has A to B to C to D back to A. So it's this scrawny little parallelogram that almost looks like just kind of lips turned sideways. But let's see if it's going to let me write on it. I don't know if it'll let me write on it. And let's do this. I'm going to exaggerate it. I want you to be a little bigger. Okay. So I'm going to recopy this graph over here so that we can draw and talk. So what we have is we've got a pressure volume diagram, and you've got point A and point B and point C and point D, and you have these graphs, A to B, B to C, C to D, and D back up to A. So I've kind of spread everything out so it's easier to see, okay? So none of these curves are isobars None of these curves are isocores because nobody is a horizontal line, nobody's a vertical line. The question is, are some of these adiabats or are they isotherms? So do we keep constant temperature or are we changing everybody? Okay, so let's look at what we say. Up here at point A, we have what they call P original. And they have that goes down here with V0. So this point is V0, P0. This point, they don't tell us what it is, except that it's at 2V0, but they don't tell us the pressure, okay? C, they tell us, C is we don't know the volume or the pressure, so we don't know either coordinate there. And D, we also don't know either coordinate, okay? So we know some of these, but we don't know the other ones. When we do this, they ask us, they're going to give us some instructions on the other part. So it says A to B is constant temperature. A to B is a constant temperature, so this is an isothermic. Because they tell me in the problem that that's going to be a temperature of 500 Kelvin. Then they tell me B to C is adiabatic. I probably would have guessed B to C is adiabatic. Why? Because the vertical drop is much bigger than the horizontal change. I see a big vertical drop, but just a little horizontal change. What does it look like on A to B though? About the same amount you move over this way, you also move this way. Does that make sense? It should sort of look a little bit like a rectangle. Okay. So if this is an isotherm, we're going to figure out what these other points are. This is an adiabat. They tell us that this C to D is also an isotherm, and it's going to be at 200 Celsius. Why would I know it has to be at a smaller temperature than A to B? Why does C to D have to be a smaller temperature? It's closer to the origin. It's closer into the axes. Okay. So that's what we're looking for on that. And then the last one is also D to A is also an adiabat. Okay. So let's go about what kinds of questions they're going to ask, because you're going to see one of these on the test. I just don't know what, which form it's going to look like, but it's going to look like this. They're going to give you a graph and they're going to ask you several questions. Okay. So the first one says, during the process A to B, the volume of the gas increases from V0 to 2V0, which we see, and the gas absorbs 1,000 joules of heat. What is the pressure at point B? Okay, so A to B, we stay at a same temp. So the rule we're going to want to use here, and in your first choice should almost always be P1 V1 over T1 equals P2 V2 over T2. So P1 V1 over T1 equals P2 T2 P2 V2 over T2. So we can cancel out these two because it's a same temp. So if P original goes with V original, what is P final when we know this one is twice as big? So the V zeros cancel out and I get P final must be 1/2 of P original. That's it. That's all you had to do. Now I would probably, in the AP test, I probably would label that as PB because they asked me at point B. You'll do a lot of that kind of stuff. Like that kind of problem is pretty common. Okay. Using the first law of thermodynamics, determine the work performed on the gas during the process AB. Okay. So now we have to stop and think, what is the law of first law of thermodynamics? The first law of thermo says the change in internal energy is equal to heat added. Make that a little bit bigger. Sorry, didn't mean to be writing so small. Change in internal energy is equal to the heat added or lost plus the work done. So what are we told about the heat added? I look back up here and I can see that right here it says the gas absorbs 1,000 joules of heat energy. Okay? The gas absorbs 1,000 joules. So would we make the Q positive or negative? Did our internal energy go up, or does our energy of our system go down if we absorb heat energy? If you absorb heat energy, your system now has more energy than it had a minute ago. So Q will be positive. More heat energy, more energy in the system. So this piece is plus 1,000. Okay? They ask me to figure out the work done. Determine the work. Well, that must mean I know what this guy is. How can I find that guy? Hey, that's one of those other formulas I said we might need. What is our temperature at point B? Well, it's the same temperature at point A. What was the temperature? I look over here and I see that temperature is 500 Kelvin. 500 Kelvin. So I come down here and go, okay. Delta U equals 3/2 times a constant times temperature. And then I pull out my ever-present trusty formula sheet. Let's look at that for just a second. I'll show you where to find these. The best part about the equation sheet is it is grouped by topic. So fluid mechanics and thermal physics are all right here. So here's where we have to think physics. What is the internal energy? When we say the internal energy of a substance, what is the internal energy? What are we measuring? It is a potential. We write it as potential because that energy is stored inside of it. But we're actually measuring the kinetic energy of the particles. So on the AP formula sheet, they do not list this as delta U. They do in the first law, but they do not when you see it in the real thing. They put it as the kinetic energy. The internal kinetic energy is 3/2 kT. But this K, and I really hate this, by the way, this K is this delta U. Because the kinetic energy of the particles is the stored internal energy of the object. I know. I'm getting a little crinkly. For those of you that are not here, I'm getting a lot of the crinkly face look. Like, why are you doing that? So internal kinetic energy, how much internal kinetic energy does my water have? Well, it depends on the temperature, because the temperature tells me how fast the little water molecules are moving. And since it's internal to the object, even though they're moving in its kinetic energy, it's internal energy for this jug of water. So we call it stored energy inside the jug of water. Okay, so delta K and delta U are the same piece of information. All right, I wanted you to see that because that's upsetting. So it has KB, so that means it's a constant, which means I have to scroll back up here and go, hey, it's a constant. Find the constant, find the constant. Find the constant. Hey, there it is. 1.38 times 10 to the negative 23rd joules per Kelvin. Okay. but this is 1,000. And that, if I put something times 10 to the negative 23rd here, I have a problem because that number is going to be this big. So what else do I need to understand here? What else might I need to understand here? Let's go back to my question. What might I need to understand? Yeah, I've got to get from temperature to energy is what the problem is here. Yeah. And if I use the Boltzmann's constant goes with number of particles. And so do I know how many particles I have? No, but I might need to know that since I'm using joules per Kelvin. Let me just show you what I'm trying to get you to think about. If I put in Boltzmann's constant here, it's 1.38 times 10 to the negative 23rd. I have to look. 1.38 times 10 to the negative 3rd joules per Kelvin. And this would be 500. So what happens to this number? This power right here makes it unbelievably tiny, right? So what would happen if I add 1,000 to it? Essentially, I'd still have 1,000, right? It's like saying I have no internal energy, sort of. It's so small. But I know it's got internal energy. So what's the holdup here? Any thoughts? Let's come back over here. Okay. Let me tell you what thought you should have. This is a change in energy, right? It occurs because a change of temperature. Like if I heat my jug, what happens to the motion of the particles? They go faster, which means I would have more stored internal energy, yes? But I was isothermic, so did I change the temperature? I did not change the temperature, which means I don't even have to use this formula because this piece is actually a delta T. If I don't change the temperature, I don't change the internal energy. Okay? If I don't change the temperature, I don't change the internal energy. So in fact, let's go back and start over. So now that you've seen what I'm trying to get pointed out here, this says in the problem, I'm going to pull the problem back up. It says during the process AB, we're an isotherm. We didn't change temperature. So when I think to myself, I didn't change temperature, here's what I do. Delta U equals Q plus W. Delta U is 0 because I didn't change temperature. No temp change. But my gas absorbs energy. So that's a positive, which means what's the work done? Yeah, that's a tough one. You subtract 1,000 on both sides and you get negative 1,000 joules. What does that mean? That the work is negative means what? Did I take in work or did I put out work? I put work out. So I took in heat and I did work out. Okay? Okay. And it'll take us a while. We'll do several of these, so don't get uptight yet. Okay? So let's look at the next part of the question. The next part of the question says, using the process AB, does the entropy of the gas increase, decrease, or remain unchanged? Justify your answer. Oh no, entropy. Entropy is the probability that I can find my heat. It's a probability of how easily can I find my heat. So if I took heat from outside in this room and I shoved it into my gas, would I be easier to find the heat or harder to find the heat? If all the heat energy was out here in my room, and then heat energy goes in here because we move from warm to cold. So I take this out of the fridge and I put it in the room and I set it down. What's going to happen? Heat energy from all over the room is going to go from hot to cold and make my water get warmer. So did my entropy go up or go down? My entropy went down. It went down because let's say little Joe Bob is this particle right here of heat energy. Little Joe Bob could be anywhere in the room to start with. But once the heat energy goes into the water bottle, there's less room for him to hide. Now I don't have to look in the whole room for Joe Bob. I can just look in the water bottle. Does that make sense? Now, if we'd done it the other way, if I had a mug of hot cocoa and I put the mug of hot cocoa on the desk, what happens to the cocoa? Heat goes out because the cocoa is warmer than the room, so the heat energy leaves my coffee cup. Now the entropy went up because all the heat energy was here, and now the heat energy is out there. So entropy is a measure of how spread out the heat energy is. So if you squish heat energy into a small space, you're increasing the likelihood to find it, so you're decreasing entropy. It's easy to find, it all got caught here. But if your heat energy flows out into a bigger space, then your entropy goes up because it's harder to find the person you're looking for. Is that kind of okay? So entropy going up means heat is more spread out. Entropy going down means heat is less spread out. It's more localized. So in the question here, what do we have? Did we change temperature? No, but we gained energy. Our gas gained energy. So this small area, the entropy actually decreased because we now know where to look for our heat. It's trapped. It's easier to find. Okay? All right. So that's letter C. And then last but not least, D and E. Calculate the heat given off by the gas in the process C to D. Well, let's see. C to D is also it's also a constant temperature. So when I write my law, changing internal energy is Q plus W. If I don't change temperature, this is 0. And they tell me what happens in C to D. Which way are we moving on our picture now? To the same place? How are we going to figure this piece out? If I'm looking for Q, that must mean I know how to find work. Okay. So let me hang on just a second. Calculate the heat given off by the gas in the process C to D. C to D does not match A to D, A to B. So we can't just go, oh, it was 1,000 joules coming in, so now it's 1,000 joules going out. What are we going to have to do to figure that piece out? We didn't change temperature, so we can't use the temperature calculation. What else might we do? It's okay if you don't know, because this is our first day to work this kind of problem, and they're hard when you first see them. Okay, well, I'm going to hang on to that then. So we need to help with 4. What about number 5? During a full cycle, is the total work performed on the gas by its surroundings positive, negative, or 0? Okay, this is an easy one. Okay. Is the total work positive, negative, or 0? The work equals area. So from A to B, we do this energy. We do this amount of work. Okay. So blue is work done by gas. The gas expands. The gas expands. If the gas expands, it pushes energy out into the world. Just like in your car, when the piston fires, the spreading out of the gas causes the piston to move, which causes your motor to turn over. Like, that's way too simplified, but you know what I mean. So that's work going out. This is energy lost by system. By system. What about B to C? Well, B to C is also gas expands. So we're doing work out on the environment, right? When do we take work in from the environment? When I go the other way. When I compress the gas. Because does a gas compress naturally? Is it normal that a gas would get smaller? No. So this part, where I compress the gas, is now work on the gas to compress. So I do work there, and I do work here. Which area is bigger, blue or pink? So blue, which means that our answer to part D would be more energy leaves than is added. So the work on the gas is negative. So here's how this works. The gas does more work out. The energy goes out. More energy goes out to the surroundings. So the gas does more work on the surroundings than the surroundings do work on the gas. So this would be what's called a heat engine. Energy flows out. Okay? Yeah.
If you're going to increase the temperature, like basically move those like things out, right?
Yeah.
You're saying that if we move out, then wouldn't the energy that the gas on the area around you be more?
Yeah, it could be. Yeah, depending on how your shape fits, yeah. But typically you have, and I'm going to show you another one. Typically they make it look pretty obvious on this. So if you're comparing this energy movement to this energy movement, you can see that that's higher on the scale.
Yeah.
Higher on the scale would mean we have more doing whatever that process is. If the gas is expanding, it's more work out. If the gas is compressing, it's more work in. So in fact, you can actually use the idea of clockwise and counterclockwise. So if you go out, let's see if I can find what I'm looking for. If you have more that goes out than in, what was I going to say? Have more that goes out than in, you've got, hang on just a second. More out than in is called a heat engine, and you're moving counterclockwise, or you're moving clockwise. If you're moving counterclockwise, that would be more energy in than out. And so you would get, where am I? What the heck? Sorry, I'm losing track. So yeah, so a clockwise motion, and I'm going to draw that. Let me get over there. Okay, that's thermal, that's fluids. Fluids. I just want to get back to where I was. Just let me go home. So let's talk about that as a general thing. So in this process, if you go X to Y to Z, which is what the arrows show, if you go X to Y to Z, you expand at low pressure. So energy is going out. The energy would be going out between X and Y, the little rectangle that's below X and Y and trapped by the X axis. When do you compress the gas? When do you make the volume go back down? From Z to X. Since Z to X is higher than X to Y, more work is going out or coming into the system than was going out. So yeah, you can think of it like that. Like, let me grab this real quick. Stay. So here to here, you only get this little block of energy. That's the energy that's the work that the gas does. Z and X would be all of the triangle plus that box. And so more work would be done compressing than work expanding. So surroundings do more work. Surroundings compress rather than the work doing the gas. Is that better?
Yeah.
Okay. Okay, folks out there, you want to chat something or you got questions? I'll wait for a second because they can ask questions anytime, but I want you to know you can too. So basically, to go back to what we're saying on this, if the process, which direction is this, clockwise or counterclockwise? Counterclockwise. Counterclockwise is always going to have more work coming in than going out. This is a refrigerator. This is a refrigerator. The one we just did, and let's look at this one down here. Let me get, not that one because it's got too many lines in it. This one is a clockwise flow. So your area would be these 3 blocks, these 3 blocks, that triangle, and those 2 blocks. That's where you're expanding. So you would use all of this area would be work going out. The work coming in would just be those 2 blocks. So this one is a heat engine. So clockwise is a heat engine, more out than in. Counterclockwise is a refrigerator, more in than out. Because refrigerating something, that's not how things don't naturally flow to cold. So you have to do more work to make it get colder, which is kind of weird. Okay, so any of you guys out there got a question? So I'm going to let us stop and breathe and work on some 10C and 10D for a little bit. And then we're going to do some more of this because we'll have to do another problem or two. But we need to stop for a minute and breathe. So, okay. You're awfully quiet. Okay, so 10C. 10C or 10D, anybody want to ask about those? And you're always welcome to get up and move around if you need to, because just don't hover over somebody for more than 15 minutes. I know we're all falling asleep today. I don't take that personally. I just know that you guys work really hard and you're all exhausted. I know.
Raise my head up for the entire lesson of learning.
Yeah.
And that's like number 4 of the question, I think.
10C number 3 is the first one they ask about. Okay.
Yeah.
I have a copy of that. I'm looking for my copy of it. Oh, there it is. Okay. Okay. So on 10, Tennessee. 10C number 3. Okay. One of the nuclear generator, the biggest nuclear generator in the world is in Lithuania, which is surprising. I think we've done this one in class, yeah? Okay, well, they haven't seen it, so I'll do that one. You guys can think about one you want to go work too. So what we've got is on number 3, it's working at a power of 1.450 times 10 to the 9th watts. And a watt is a joule per second. So they ask us, we've got this mass of steel, 25.1 times 10 to the 9th kilograms of steel. And we want to put this in a big vat and take water. And the water's, so here's what we've got. This is how I work these problems. What do I need to do? Let me move this over because y'all can't see that very good, I see. Okay. I have the heat, 1% of the heat lost by steel. Added to the heat gain of water has to be equal to 0. We have to conserve energy. So whatever the steel loses, the water has to gain. And they asked me, what temperature, what is the temperature change of the steel? So I've got heat lost by steel. I've got heat gained by water. So this is going to be MC delta T plus MC delta T, where this is steel and this is water. And that's going to add up to 0. But they don't tell me the mass of the, let's see, the water, right? Okay, so they're going to tell us this one. But they told it to us as a power rating. So here's what's going to happen. Mass of steel, 25.1 times 10 to the 9th. Specific heat of steel, what did we say that was? 386, 380, I don't remember. $490. Okay. So 490 And change in temperature, I don't know. And this piece, the MC delta T for the water, is 1%, which is 0.01, times 1.45 times 10 to the 9th joules per second. So I have to do a unit conversion. 3,600 seconds in 1 hour, 24 hours in 1 day, 365.25 days in a year. So this is the energy for 1 year. And then I take 1% of it. And that all equals 0. So I think, you should be able to finish it from there. So you've got whatever this comes out, delta T, and whatever number that is will equal 0. So that's how that one gets set up. So basically it's one big unit conversion. And I'll wait to see if you got questions. Is there another one on 10C that you guys want to work or look at? Let's see. I got you on the not being able to see it. Let me zoom. Can you see it better now? All I'm doing is, okay. So let me rewrite it for you. .450 joules per second. Whoops. Times 10 to the 9th joules per second. 3,600 seconds in 1 hour. 24 hours in 1 day. 365.25 days in 1 year. That's the energy for a year. Is that better, Jazz? Okay. That's yours from last quarter. I graded it, but it's not. I don't really have to grade on everything just so that it's not. There's the hatchback. Orange folder. Orange folder for everything turned in today. Okay, anything else on 10C? People here or people there? Okay, what about 10D? 10D. Yep, it's right there, it's fine. Anything on 10D? 10D number 5. Ah, the gold bars in Fort Knox. Okay. 10D number 5. Okay, so 500,000 standard mint gold bars, each with a mass of 12.4414 kilograms of gold. And assuming an initial bar temperature at 5 degrees Celsius Each bar will melt if it absorbs 2.5 million joules of energy. Okay. So what do they want us to do? If the specific heat of gold is this, and the melting point of gold is 1063, calculate the heat of fusion of gold. Okay, so what do we need to do? First, we need to get the gold up to 1063 because we got to heat it up. Then what do we have to do? Then we're going to melt the gold. So our formula will be heat the gold up plus melt the gold. So M is 12.4414. No, you're just doing one bar, assuming an initial bar temperature. So you're just doing one bar. And then the specific heat of gold is 129. And the temperature change is 1063 minus 5. Then you're going to have 1 bar of gold, HF equals 2.5, is it million? Megajoules, 10 to the 6th. So there's your Q. So this number just comes out a number, and you know the number on the other side, they tell you how much total energy was used. So all you've got left is to find the heat of fusion. So I'll let you finish it from there. And yes, it was just 1 gold bar, not 500,000 gold bars. Although if you had done 500,000 gold bars, I'd still count it right, because I can see how that could happen. Just so you know that each bar of gold is something like 27 pounds. So it's not like you run in Fort Knox and grab 3 or 4 gold bars and run out with them.
You need more than 1 gold bar.
No. But if you're going to fill a backpack with them, you're not filling it with like 10 or 12.
That's the one thing.
You're like 3 gold bars. I can do that. Yeah. Oh, yeah. You could get one of those little, you could get a little suitcase on wheels. You could carry some more that way.
Move a seat. Break an axle.
Yeah, you'd probably break an axle. That's probably true.
When they like throw these bags of money, like,
I know, that's,
there's nothing.
it's one of those things that makes me laugh in movies, because everybody thinks like you go in there and you see all the gold bars and you just stack them in a backpack or something and you carry them. Like, gold is really, really, really dense. Just to give you an idea, since we're waiting to see if there's another question, if you were to take 10 grams of gold, you guys remember the little 10 grams that were about this big? If you took 10 grams of gold and you hammered it out, you could hammer it. There's enough gold in it. It's so dense that you could hammer it out and it'd cover an entire football field. And it would be, several atoms thick. It wouldn't just be like one layer of atoms. It would be like a very thin gold sheet. So crazy that gold is that malleable is the word we use for that. But yeah, you probably wouldn't need more than 1 gold bar, because what's gold going for, like $600 an ounce or something right now? It's expensive.
You can get all 1 or 2 gold bars.
Yeah, but you're not like taking the stack of the gold bars and you're dumping it in your backpack and you're, bills, even if you take those stacks that they show in the movies of bills get pretty heavy pretty quickly too.
Like, and they were running
Yeah.
with like body armor and like bags of money.
Right. I will say this, that in the military, you have to be able to carry, 60 pound backpack? Isn't that what they usually use as the standard size when you're when you're training.
Yeah, but I think we all know when they go up on the woods, they carry a lot more than that.
Yeah,
They've been-
but still 60 pounds, just thinking about carrying 60 pounds is a lot of weight. Because what they tell us in hiking is that for every 1 pound of weight you have in your backpack, it feels like 4 pounds of weight on your legs because of the way you're holding it. Even the backpacks that have sort of an internal structure to help support. And so it's crazy. It'd be like you now weigh 240 pounds and you have to lug that around for 7, 8, 9, 10 miles.
I think it's recommended like 20 to like 30 pounds.
Yeah. Yeah. My backpack, my big one for backpacking, like backcountry backpacking, is I think a 30 liter is the way they do it. But 30, if it was filled with water, I wouldn't be able to carry it because water's really stinking heavy. Like my day pack holds 2.5 liters of water, like a Camelback in it. But 2.5 liters of water feels like a lot when you're lugging it around. The good news is the more you drink of it, the lighter the backpack gets. But yeah, 60 pounds, nuts. Yeah, and all of you, Jasmine said, remember how all of us in Raiders had to carry the water jug? Yeah. And that's just 1 gallon, right? Oh no, you guys are using the big water ones. Okay, yeah.
You just pick it up, like put it on your shoulders.
Uh-huh.
Start running.
Okay. Yeah,
So they were heavy.
that's kind of nuts.
And then the backpack.
But it is quite a lot. And gold, of course, being very dense is one of those things. But it's really interesting that gold changes temperature really easily, right? 129, like water's specific heat is 4,186. Gold's is 129. So guess who's going to change temperature really easily? Gold. Oh, and Rachel said, don't forget about the sandbag week. We're having our reminiscence of how miserable these things are. See, now you woke up my class.
Grover.
Any other questions you guys have on this?
They started running out of love.
I know.
I'll stick on stretcher. I'll stick on stretcher. That help, I literally-
You guys all right? Okay. All right.
Does it come to like around 6,440?
Uh-huh. Yeah.
I just want to make sure.
Yeah, the number, so when you do heats of fusion and heats of vaporization, most of the heats of fusion are like in the 10,000s, high thousands to 10,000s, and the heats of vaporization tend to be in the 10,000s to 100,000s. So it takes a lot more energy to vaporize than it does to melt. And remember, of course, that if you're giving that energy off, if you're losing the energy, you're going from gas to liquid or liquid to solid. And the number's the same whether you go phase up or phase down.
What if you were to like skip 2 phases?
Like sublimation, like a solid carbon dioxide, dry ice. Dry ice goes straight to liquid form. I mean, it goes straight to gaseous form. And so there is a number for that, and it's more in the 100,000s because you're skipping a phase. But what's really weird is if you watch burning logs on slow-mo, logs will actually start to sweat. So there'll be a little bit of the sap coming out and some of those things, but the wood itself will actually sweat the wood out of in between the particles. And so it kind of sweats for a little bit and then it burns. So it kind of does do a liquid phase in the middle, but not for very long, which is weird because I didn't believe that until I saw it. Like, ooh, that's crazy. Dry ice is fun. It doesn't smell all that great though.
Like, I like the little, you get a piece of dry ice and
Uh-huh.
you get a bottle of water. Like,
Yeah.
You have to add a little bit of it and
Uh-huh.
you just drop that dry ice.
Screw it.
Quick and
And then it makes like a smoke bomb. Yeah.
And then it's a lot though.
Yeah.
Oh my gosh, the dude took like 7 plates of dry ice and shot him with a 50 That was cool. I mean, just
Let me get a
massive,
demolition or.
massive CO2 cloud.
These are-
Huge.
We're now relating all the things that we can do that are crazy with dry ice. All right. So if you guys don't have any other questions, then I'm going to call it for today. And tomorrow we'll work another one of these, and then I'm going to give you some practice problems. But we do have, before I forget. Oh, I made 2 windows. Way to go. Before I forget, let's look at our calendar. That's not your calendar. That's Physics 1. So real quick on the calendar, I haven't gotten this quiz made out yet, and I'm really sorry about that. I'll get that done maybe tonight or tomorrow night. So calorimetry practice problems in 10C, 10D. I need to see them by today, no later than tomorrow if you can help it. And then on the 20th, which is today, I had that we're going to do a quiz. We're going to move this quiz to Thursday. So the calorimetry quiz will be on Thursday, and I'm going to do you got some book problems too, but you may want to wait till we do a few more examples on this before you go into the book problems and the homework, okay? So quiz on Thursday, the quiz will be on calorimetry, which is what we've been doing on 10C and 10D, and then the thermal expansion, which I'll give you the formulas for, so you just need to mostly be able to talk about it. Okay? All right. Other than that, y'all can hang out or go. Is the recording going to be posted? Yes, I'm recording it, so I'm going to post it on YouTube. When it comes back up, I'll post it on my YouTube channel for tonight. Yeah. Yep. You guys have any other questions out there? Yep. Good stuff. Yes, Eric. Page 391. Okay. The ones we were talking about yesterday, yes? Okay, 27, 393, 27. Okay. So 393, so I thought you could figure out what you couldn't. So what you do is, what kind of process is it? Since it's a horizontal line, it's isobaric. What is the final temperature? What you're going to do is you're going to do the P1 V1 over T1 equals P2 V2 over T2 and use the ideal gas law. So we're going to start with, and now I don't have any paper showing. Great. So you have this. It's an isobar. So P1 V1 over T1 turns into P2 V2 over T2. Okay, it's isobaric, which means that your pressure cancels out. But to be able to use this, you have to know one of your starting temperatures. So what you're going to have to do is pick one of the 2 points. Okay, so they tell us on 27, the initial temperature is 900 Celsius. And so the initial temperature was at 300 volume and 3 pressure. So PV equals nRT. Pressure was 3. Volume was 300. Oh, wait. Sorry, they told us that already. We don't have to use this. Our initial was 300 volume, and our initial temperature was 900 Celsius. But we can't use Celsius. We have to use Kelvin on this. So 900 Celsius plus 273 is 1173. You knew your new volume is 100. So this is how you can find T2. Is what we were just doing using the combined gas laws. And then how many moles of gas there are, that's when you go to the you go to the PV equals number of moles, K Boltzmann's temperature. And you can pick either one of those, either one of the two spots you can use because they'll have to be the same. Yeah, you can't use, the reason you can't use Celsius is because temperature's in the denominator and Celsius has a 0. So we don't ever use Celsius for the combined gas law. Okay, good stuff. All right. I'll sit down so I'm not standing in front of the picture. And then I'll cut this off here in just a minute or two if there are any other questions. Luke, that cookie was amazing.
Oh, yeah. They're really good.
560 calories,
Uh-huh.
but it was ridiculously yummy. Thank you.